I want you to imagine a completely absurd scenario for a second.
Okay, lay it on me.
Imagine you buy a brand new smartphone. You take it out of the box, you turn it on, and before you can actually do anything at all, before you can even make a call, the phone has to locally download and store the entire internet.
Oh, wow. And I mean, not just a summary, you mean every single byte of it.
Exactly. Every YouTube video ever uploaded, every Wikipedia article in every language, every single person's Gmail inbox, like it all has to be saved directly onto that little piece of metal and glass in your hand just so the device can function.
Right, which is, it's a fun thought experiment, but obviously an impossible premise. I mean, you'd need a device with infinite storage.
Yeah, totally.
And even if you had that, the second someone, like anywhere in the world, uploaded a new video, every single phone on Earth would have to just freeze, sync up, and download that new file simultaneously.
Which would completely break the laws of physics.
Yeah, absolutely.
Yeah. But because that doesn't happen, we take the alternative completely for granted. I mean, we just open our phones, we tap a piece of glass, and the entire world is instantly right there.
It really is magic when you think about it.
It is. And so today, we're doing a deep dive into the invisible scaffolding underneath that exact experience client-server architecture.
Right.
Which, I know, it sounds like dry technical jargon, but I promise, understanding this one dynamic completely changes how you look at the apps on your phone. We're going to break down how this system evolved, pause time to look at the split-second conversations happening under your fingertips, and basically figure out how the internet actually functions.
Yeah, and it really is the master pattern of the modern world. I mean, whether you are streaming a movie on your television, checking your bank balance, or just, sending a text message, you are relying on this exact same division of labor. Understanding this one architectural choice unlocks almost everything else in tech.
So before we talk about massive global networks and like giant server farms, we have to look at the micro level. Because underneath all the complexity, this is just a relationship between two pieces of software, right? A talker and a listener.
That's the foundation, yeah. On one side, you have the client, and the client is the program that initiates a request. It wants something.
Right.
On the other side, you have the server. The server is the program that basically just sits there, listens, and responds to that request. One asks, the other answers.
A really great way to visualize this, and this helped me a lot, is like walking into a busy diner.
Oh, yeah. The diner analogy is perfect.
Right. So you, sitting at the booth, you are the client. You look at the menu, figure out what you want, and place an order. The kitchen in the back, that's the server. They receive your order, prepare the food, and send it out to your table.
And the crucial part of that diner dynamic is the strict boundary between those two roles. As the customer, the client, you have no idea how to cook the meal.
I definitely don't.
Right, you don't know what temperature the stove is set to or what ingredients are stocked in the pantry. You just need to know what you are allowed to ask for, the menu, and how to ask for it.
And the kitchen staff, they don't care who you are. They aren't coming out to your booth to chat about your day. They just receive a valid order ticket, process it, and fulfill it.
Exactly.
So let's make this real for you listening right now. When you open up Instagram while you're standing in line for coffee, your app is the client. It essentially walks up to the diner counter and says, show me my feed.
Right, and the Instagram server in some data center somewhere receives that request. It checks your identity, queries a massive database to figure out what posts your friends made in the last hour, packages up all those images, videos, and captions, and ships them back.
Just serving the meal.
Exactly. The client, your app, receives that raw package and does the heavy lifting of arranging it beautifully on your screen. And this dance happens billions of times a day, usually in under a second.
Now, I do want to clarify a distinction here, because it actually took me a minute to wrap my head around it. When we say client, my brain instinctively pictures the physical object. Like, I think my laptop is the client, or my iPhone is the client.
That is a very common mix-up. But the metal and glass box in your hand is not the client. A client is strictly software.
Okay.
Your web browser is a client. The Spotify app is a client. If you have a smart thermostat on your wall that pulls down tomorrow's weather forecast, the tiny piece of code inside that plastic box is acting as a client.
So my phone is just the house that the client lives in.
Precisely. The client is the software making the request.
Okay, that makes sense. Now, this elegant division of labor, the requester and the responder, it didn't just magically appear on day one of the computer age. Tech actually had to be forced into this model over a few decades to solve some massive logistical nightmares.
Yeah, the history of computing is really a pendulum swinging back and forth between centralized control and decentralized power. If you go back to the 1960s and 1970s, the client-server model just didn't exist. We were in the mainframe era.
Right, the room-sized computers with those spinning magnetic tape drives that you see in old NASA movies.
Yeah, exactly those. A university or a large corporation would have one of those giant mainframes sitting in a basement somewhere. And the users sitting at their desks didn't actually have computers. They had what were called dumb terminals.
Wait, dumb terminals, meaning what, exactly?
Meaning it was literally just a cathode ray tube screen and a keyboard. They had zero processing power of their own. Every single time you pressed a key, that electrical signal had to travel across a wire down to the basement. The mainframe did all the thinking and then sent the visual result back up to the screen.
Wow, meaning if the mainframe went down, the entire building was instantly paralyzed.
Everyone was offline. It was completely centralized.
Okay, so then the 1980s roll around, the personal computer is invented, and the pendulum swings the other way. Suddenly, an accountant has real computing power sitting right on their desk. They can run a spreadsheet locally without relying on a basement mainframe.
But that created a whole new problem. Those early PCs were basically isolated islands. You could run a spreadsheet, sure, but you couldn't easily pull down the company's master inventory data.
Right, because nothing was connected.
Exactly. So businesses realized they needed a hybrid approach. Keep the central database on a shared server, but let the powerful new PC handle the user interface and the local math. That was the true birth of the client-server split.
But they hit a massive wall with that too, didn't they? Because by the early 1990s, they were using this two-tier architecture. You had a bulky software program installed on a Windows PC that connected directly to a database, which sounds fine until you realize the software on the PC held all the business rules.
Yeah, and that's where the logistical nightmare really begins. Let's say your company changes a pricing policy or the government updates a tax code.
Oh, wow. So if the tax math lives inside the software on the desk, the IT department literally has to walk around with a stack of floppy disks and manually install the update on 4,000 individual computers.
It was completely unsustainable. You couldn't roll out new features quickly, and if one single PC missed the update, their outdated math would corrupt the whole central database.
Yikes.
This bottleneck is exactly what the World Wide Web solved in the mid-1990s. The web revolutionized architecture by making the web browser a universal client.
So the browser is essentially a blank slate. You didn't have to install a custom floppy disk program for every single task. The rules, the math, and the data all move back to the server.
Precisely. The server just sends over a document with some instructions and the browser reads it. If a company updated their tax rules, they just updated their central server.
That's brilliant.
Right. The very next time you visited the website, your browser downloaded the updated page instantly. That manual deployment nightmare just vanished overnight.
Which explains why things shifted again in the 2010s. Because suddenly, we weren't just serving web pages to browsers anymore. A company like Netflix has an iPhone app, an Android app, a web app, and an app on your smart TV.
And building a completely different server to cater to each of those specific devices would be a nightmare. So developers moved to an API-first world.
API meaning Application Programming Interface.
Yeah. It's basically a universal plug socket. Developers build one clean, central API on the server. Now, instead of sending a fully designed web page with colors and fonts, the server just sends raw data.
And lets the client figure out how to draw it. So the iPhone app takes that raw data and makes it look like an iPhone screen. And the TV app takes the exact same data and makes it look good on a 65-inch screen.
Exactly. It completely decouples the data from the presentation.
So we've gone from one giant brain in a basement to a bunch of disconnected brains on desks to this massive hive mind where highly specialized brains seamlessly trade raw data.
I like that analogy.
And the way those brains communicate is what I really want to dig into next. The request-response cycle. This is the actual heartbeat of the internet. If we freeze time for a millisecond, how does this actually work when someone taps a link?
Well, every single action, clicking a link, liking a post, submitting a password, forces the client to build a formal request. And that request has three distinct anatomical parts. First is the destination, which is the URL. It acts as a precise global coordinate.
Okay, got it.
Second is the method, which is basically the verb. Are you asking to get data, post new data, put an update to an existing file, or delete something?
So get is reading, post is writing.
Usually, yes. And then the third part is the payload and headers. If you are submitting a login form, your email and password are the payload. The headers are the invisible metadata, like the client telling the server, hey, I'm using Safari on an iPhone and I prefer English.
So the client packages all this up, and then the physical journey begins. Because it's not just magic. Your phone converts that request into radio waves, beams it to a cell tower, which converts it into pulses of light shooting down fiber optic cables.
Yeah, the physical reality of it is wild.
Right. It bounces through dozens of routers, crossing state lines, maybe even traveling through thick cables sitting on the floor of the Atlantic Ocean until it reaches a data center. And that entire journey often takes under 50 milliseconds.
Which is astonishing given the physical distances involved. Now, once the request actually arrives at the data center, it usually hits a load balancer. Think of a load balancer as a digital traffic cop.
Okay.
It looks at the incoming request and says, server A is too busy, let's route this to server B. Server B does the actual math, talks to the database, and forms a response.
And the response mirrors the request, right?
Yeah.
It also has three parts: a status code, headers, and a body.
Exactly. Everyone is familiar with the famous 404 not found status code.
Oh, yeah. The classic broken link.
Right. The 400 level codes mean the client made a mistake, like asking for a page that doesn't exist. A 200 code means success. A 500 code means the server itself had an internal meltdown. It's a universal numerical vocabulary, so the client instantly knows the outcome. If it's a 200 success, the server includes the body, which is the actual data you asked for.
Let's trace a real example to make this concrete. You type youtube.com into your browser and hit enter. Your browser fires off a GET-T request. It hits the load balancer, server B processes it, and sends back a 200 success code with an HTML body.
Yes, but here's the crazy part. HTML is just a skeleton. It's really just text. So your browser starts reading that text from top to bottom and it realizes, oh wait, I don't have the thumbnail image for this video. I don't have the CSS code to make the background dark mode. I don't have the raw JSON data for the comment section.
So it's missing all the actual content.
Right. The page you see loading isn't one request-response cycle. It's a massive cascade. The browser reads the initial HTML, panics about all the missing pieces, and instantly fires off 50 or 100 new GET-T requests to fetch the images, the fonts, and the layout files.
All completing in the span of a second or two, just to render one single screen.
It's a beautifully orchestrated explosion of requests.
But this brings up a massive conceptual hurdle, I think, because the entire request response cycle is stateless by default, which basically means the server has profound amnesia.
That's a great way to put it.
Right. It answers your request for a YouTube video, and then a millisecond later, it completely forgets you exist. The next time you click something, it treats you like a total stranger.
The server wakes up every single morning with no memory of yesterday.
Right. So if the server has zero memory of our previous interactions, how does my bank keep me logged in while I'm clicking around my checking and savings accounts?
Well, a great way to think about this is the movie 50 First Dates.
Oh, I love that.
Because the server has amnesia, the burden of memory falls entirely on the client. To stay logged in, your browser has to bring a photo album every single time it talks to the server to prove its identity.
So every single time I click a new page on the banking site, my browser is essentially reintroducing me.
Yes, usually in the form of a session token or a cookie, which gets passed in those invisible headers we talked about earlier. Your browser saying, hi, I'm user 42. Here is my encrypted token proving I logged in 10 minutes ago. Please show me my checking account.
Wow.
Then you click savings, and the browser says, hi again, I'm user 42. Here's my token. Show me my savings.
That sounds incredibly repetitive for the client. Why not just program the server to remember people?
Because memory takes up RAM, and tying a user to a specific server destroys your ability to scale. Well, if server A is the only machine that remembers you are logged in, all of your traffic must go to server A. If server A crashes, you get logged out. But if your client brings the token every time, the load balancer can send your first click to server A, your second click to server B, and your third click to server C.
Ah, I see.
None of them need to remember you. They just verify the token. That stateless amnesia is the absolute secret to operating at a massive scale.
That makes perfect sense. The amnesia is a feature, not a bug. But that actually leads to the next architectural problem. If an app like an international bank is dealing with millions of requests per second, the logic on the server side must be incredibly complex. You have databases, security checks, balance verifications. How do engineers organize all that back-end chaos without the whole thing collapsing?
They do it by using tiers. Tiers are logical layers of responsibility. A good analogy is the structure of a large company.
Okay, like corporate departments.
Exactly. You have sales, which talks to the customers. You have operations, which fulfills the orders. You have finance, which holds the actual money. You wouldn't merge all those departments into one chaotic room. You separate them so they can specialize and be secured independently.
Got it. And in modern software, the gold standard is the three-tier architecture. So let's trace that $100 transfer to a friend on a banking app. The first tier is the presentation tier. That's the app on your phone. It displays the buttons and the input fields.
Right.
But when you hit send, your phone doesn't talk directly to the bank's database. It talks to the middleman, the application tier.
Yes. The application tier holds all the business logic. It checks your balance, it verifies your daily transfer limits, it runs fraud detection algorithms. If everything passes the application tier and only the application tier turns around and talks to the third tier, the data tier. That's the actual database that permanently moves the money.
I have to challenge this, though. Moving data across an air gap between two entirely different servers, the application server and the database server, that have to add latency, right? Why not just keep the business logic and the database in one super fast machine? Doesn't separating them just create a bottleneck?
It does add a fraction of a millisecond of latency, sure, but the trade-off is security and stability. By keeping them separate, the client is completely shielded from the database.
Oh, because they can never touch it directly.
Exactly. A hacker messing with your phone app can never directly query the bank's core ledger. They have to go through the application tier's strict rules. Plus, it allows for independent scaling. If it's Black Friday and everyone is checking their balance, you can spin up 50 new application servers to handle the traffic without needing to copy the massive database 50 times.
Okay, that's a great point. Security and scaling definitely beat latency. But what about giants like Amazon or Netflix? Three tiers can't possibly be enough for them.
No, they use N-tier architecture. N, just meaning as many specialized tiers as you need. They might add a caching tier, which holds the most popular movie data in ultra-fast RAM so the main database isn't bothered.
Right.
They might add a specialized search tier just to handle the search bar autocomplete.
Yeah.
Or a message queue tier to handle background tasks like sending email receipts.
But you wouldn't use N-tier for a simple personal blog.
Definitely not. Because every time you add a new boundary, you add a new point of failure. If a simple website uses 10 tiers, it's going to be fragile and expensive. The golden rule of architecture is always start simple.
So we've spent this entire time painting client-server architecture as the undisputed king of the internet. I mean, it runs the banks, the streaming services, the social networks. But there is a rebel alternative, right? A radically different way to organize a network called peer-to-peer, or P2P.
Yeah, P2P flips the whole model on its head. In client server, the roles are strictly fixed. You are a requester or you are a responder. In P2P, there are no fixed roles. Every single node on the network is equal. Your computer acts as a client and a server simultaneously.
So if client-server is a central, highly organized city library where everyone checks books out from a librarian, P2P is like a neighborhood book swap.
That's exactly it.
If you want a specific file, you don't go to a central server. Your computer just shouts out to the network, hey, does anyone have this? And whoever has pieces of it sends them directly to you.
And this leads to a fascinating scalability paradox. We just talked about how in a client-server model, a massive spike in users is a huge burden. If 1 million people visit a website at once, the central server gets crushed. But in P2P, the BitTorrent protocol, adding more users actually makes the network faster.
Because of how the files are chunked. If I want a 1 gigabyte video file, I don't download the whole thing from one neighbor. I download piece number 1 from neighbor A and piece number 2 from neighbor B.
And crucially, while you are downloading piece 2, your computer turns into a server and starts uploading piece 1 to neighbor C.
Wow.
Every person who is consuming data is simultaneously providing bandwidth to someone else. So the more people downloading, the more mini servers there are.
It's a brilliant mechanism, but it also highlights the flaw, doesn't it? In P2P, I'm directly connecting my machine to a bunch of random strangers' computers, which means there is zero central authority.
Yes. And no central authority means nobody to enforce security rules or verify identities. That is exactly why your bank is never going to use a P2P network to handle your checking account. They require the absolute control of a central server.
Right.
But if you are building something that explicitly needs to resist central control or censorship, like a cryptocurrency, for example, you rely on the decentralized nature of P2P.
And we actually use hybrid models of this every single day without even realizing it. Think about a Zoom or a Skype call.
Oh, that's a perfect example.
Right. When you first open the app and dial your coworker, your client talks to a central server. to figure out where your coworker is on the internet and to negotiate the connection.
That's classic client-server. The server is acting as the switchboard operator.
But once the call connects, bouncing heavy, real-time video and audio streams through a central server in another state would cause a massive delay. So the system just shifts. Your computer and your coworker's computer start sending the video packets directly to each other, peer-to-peer.
Right, bypassing the server entirely to keep the latency as low as possible.
It's the absolute best of both worlds. The control of a server to set the rules and the efficiency of P2P to move the heavy data.
It really is a testament to how adaptable these architectural patterns actually are.
So let's pull all of this together. The next time you are sitting on your couch, just aimlessly scrolling on your phone, I want you to remember the invisible mechanical power you are wielding. With every single tap of your thumb, your software client is orchestrating dozens of request-response cycles. You are converting data into light, navigating packets through undersea cables, bouncing off load balancers, passing through strict application tiers, pulling from databases, and bringing it all back to render on your screen in a fraction of a second.
It really is a marvel of human engineering. I mean, it's layer upon layer of problem solving over the last 60 years.
And it's not done evolving. To end today's deep dives, I want to leave you with a thought-provoking idea that really builds on all this. Right now, there is a massive push in tech toward edge computing. Companies realize that sending data to a massive centralized data center in Virginia takes way too long. So they're pushing server logic out to smaller mini data centers closer to our local neighborhoods.
Yeah, the edge of the network.
Right. But as those servers get pushed closer and closer to us, where does it stop? Will our own powerful smart home devices, our refrigerators or our cars, eventually become the edge servers processing data for our neighbors?
It really points toward a massive, futuristic, hybrid network. I mean, a world where the internet isn't just sitting in a warehouse somewhere, but is everywhere and nowhere at once.
It's like that absurd scenario we started with, downloading the whole internet onto your device. That might not be so far off after all, but instead of downloading the internet, our devices just become structural pieces of it. Thank you so much for joining us on this deep dive. We hope you look at your everyday apps with a newfound sense of wonder. Until next time.